Let's do the extra practice problems for Chapter 16. Number 1, the equilibrium constant for a particular reaction is given by K equals, and then it gives us the reactions. Remember, the products are on the top and in the numerator, and the reactants are in the denominator. So it says, what is the balanced chemical equation for this equilibrium? So once again, the reactants are in the denominator, so I'm going to go ahead and write the reactants. And notice there's no exponent there, so its stoichiometric coefficient is 1. The next one is to the 4th power, so its stoichiometric coefficient is 4. And that takes care of your reactants. And then you go to your products, which are in the numerator. Notice the first one has squared, so its stoichiometric coefficient is 2, H2S plus. The second one doesn't have an exponent, so its stoichiometric coefficient is 1. And so when we take what we were given, there we go. This is what we were given, so I knew this was the products, this being the stoichiometric coefficient. And here's your reactants, and this is our stoichiometric coefficient. So we just worked backwards. Number 2, the equilibrium constant for the following reaction is 4.18, 1 over molar squared. And we have this reaction. The equilibrium concentrations are found to be as follows, and then it gives your concentrations. What is the concentration of water vapor? Okay, so first, let's write our equilibrium constant reaction. And so we have K equals, and we take the products, and there's no stoichiometric coefficient there, so there's no exponent. And these are gases, so we can use them all. Okay, and then we do the reactants. Now this one, H2, has a stoichiometric coefficient of 3, so we're going to cube that there. Okay, so now we've written our equation out, and we know a lot of this information. We know that K equals 4.18, 1 over molar squared, and we also can plug in the numbers that we're given. And so we're given CO as 0.212 molar, and there's no exponent there. We're given H2 as 0.633 molar, but this one is cubed. Don't forget your exponents. We have CH4 given to us as 0.210 molar, no exponent. And then we are looking for the water vapor concentration. Now, I want you to notice that we are given all these numbers except for here. So all we're really doing is solving for this. So we're going to multiply both sides by this. We're going to divide both sides by that. We have 3 significant figures in each places. So we're going to end up with 1.07. That's our number. What we did was we took these two and multiplied them up here. So we had I'm looking strictly at the units now. So we had M4, this is these two, put up here, and then we're going to divide by this one. So we're going to add another M down here, so M3. So this whole thing would be molar, which is exactly what we want. And that's nice that it worked out that way. Does everybody see what I did? I started with 1 over M2. I multiply both sides by this, so that's M to the 4th. And then I divide by this, so we have another M here. I'm going to go like that. So that actually makes this M to the 3rd, doesn't it? So I'm going to go like that. M to the 3rd, and so that's going to leave us molarity. And so that should be our answer, is 1/7 molar for our water vapor. Number 3, given the information below, write each equation as a one-way reaction if possible. If not, indicate which side the equilibrium is weighted towards. All right, the first one is a very small number, and because it's a very small number, we would actually have to write the reaction with we would actually have to write it to the left because it's heavily weighted toward the reactant side because it's such a small number. But we're not allowed to leave it like this, so we actually have to flip it. So you would rewrite this and that's how you would rewrite that for it to be correct. That's A. For B, you see that K equals 27.8 per molar squared. Now this isn't huge, so we're still going to leave the equilibrium sign. We're still going to leave the equilibrium sign, but this is definitely weighted toward the product side because it is a number well above 1. Whereas the next one, C, is huge. It's so big it's huge. So you're going to rewrite that one with just the arrow going to the right-hand side because the K is so large. And then for D, it's a fractional number, but it's still not ridiculously small, and therefore we know that it's weighted toward the reactant side, but you could still write your equilibrium sign with it weighted toward the reactants. So we had A, where because it was so huge, so small, we actually flipped the whole thing and wrote the arrow from left to right, but we flipped the whole thing. For B, we saw that we could use the equilibrium sign, but it's weighted towards the products. C, it's huge number. K is a huge number, therefore we just wrote it with the arrow going to the towards the products. And on D, it's less than 0, but it's not too ridiculously small. So we still wrote the equilibrium, but here it's weighted toward the reactants. Number 4 says, write the equation for the equilibrium constant of the following reactions. So remember, when we do the equilibrium constant, we write K equals, and first you look at the products. These two products are aqueous, but the reactant is solid, and solids fall out. Remember, solids and liquids are not written in our equilibrium reactions. So this ends up just being Ag plus Br minus, and that's it. He has a little equilibrium here. I'm just not writing that, so, but that would be it because the reactant solid would fall out. Look at B. The first reactant as a solid, it would fall out. We would keep the aqueous, but at the far right-hand side, the liquid water would fall out. So for B, the only product you could use is Fe2SO4 and liquid water would disappear, and then you wouldn't use the solid reactant, so then you would have H2SO4 for the aqueous one, and that is to the third power. Don't forget that. And then if you want, you can write your little equilibriums in here. Okay, there you go. So that's A and that's B. And that's because solids and liquids, remember, they fall out, so they don't get written in here. Number 5. A chemist is studying the following reaction at 25 degrees Celsius. For each of the following situations, determine if the reaction is at equilibrium. If it isn't, indicate which way it must shift to reach equilibrium. First, let's write our equilibrium equation. So we have K equals there's no stoichiometric coefficient there. There is one for this one. So we're going to put it up here. Those are both gases. All of these are gases, so they will all be kept. We will include them. And this one has a stoichiometric coefficient of 4, so it's to the 4th power. Now, we know that this whole thing is at equilibrium at 27.8 molar. There we go, at 25 degrees. So now you're going to start plugging in. For the first one, you're going to go ahead and put 0.100 molar down here. The next thing he gives you is H2, so we're going to put that in, 0.100 molar, and that's to the fourth. And then the next one we're given is this one, so we're going to put in 0.050 molar, and no exponents there. And this next one is 0.050 molar, and we have that one squared. Okay, when you do the math on that, the answer I come up with in my calculator is 12.5, and this would be molar cubed over molar to the fifth. So this is going to cancel and leave me with 1 over molar squared. And I was supposed to write this 1 over molar squared. That's what I was having trouble with. Okay, so now we've got it at these concentrations, but this is in two significant figures, so this ends up being 13. Is 13 the same as this? Obviously not. And so this is smaller than 27. Therefore, we would have to push it toward the product side to get it to equilibrium. So for A, the answer would be shift it to the product side. Let's go to the next one. To the next one, CS is 1.1 molar. This one is 1.1 molar. This one is 2.2 molar. And this one is 4.5 molar. So when you do that, what I get here is 27.7, but I can only have two significant figures. So I'm going to go to 28. But if you look at this and you look at this, this one is at equilibrium. So B is definitely at equilibrium. That's just at equilibrium in two significant figures, and that's in three significant figures. So B is at equilibrium. Let's try C. So we put C in, 0.90 molar, 0.90 molar, 7.1 molar. Wow, those are bigger digits, that's for sure. 7.1 molar. And so you go ahead and do these, and we have two significant figures. My answer comes out as 606. So I'm going to call that 610. And once again, that will be 1 over molar squared. That is a lot larger than 27.8, and therefore this is definitely weighted too heavily toward the product side. So we're going to push this back toward the reactant side to try to bring it to equilibrium. So shift it back to the reactants to try to get it back here. Number 6. The following reaction reaches equilibrium, and so it gives us the reaction. And it gives us the enthalpy of the reaction here, and it's a negative number. So we would add that to as a positive to the product side. As you know, in this chapter, these phase symbols really matter, because remember, if we change the solid or the liquid, it's not going to affect anything else, because they don't affect when they're changed. But when we change other things, they can be affected. And remember, we are adding the energy to the product side because it's an exothermic reaction. Now let's try the questions. A, what will happen to the concentration of this if the temperature is increased? Now, if the temperature is increased, the whole reaction is going to be pushed to this side. So what's going to happen is these are going to increase and these are going to decrease if we increase this. That's our starting point. And so we were looking for this, so the answer would be that the concentration of this would decrease. B, what will happen to the concentration if F2SO4, this one, is added? So if we increase this one, Now what's going to happen? Well, it's going to push everything in this direction, so we're going to go like this, and it's going to cause this to decrease. And so we were looking for how it affected this, so this would increase, because once again, it's pushing everything in that direction. C, what will happen if we remove this? Well, if we remove this, nothing happens because that's a solid, and if we change that, it doesn't affect anything else. The same would be true if we did anything with liquid water. It wouldn't change anything. So the answer is it doesn't change anything. D, what will happen to the concentration if H2SO4, right here, if we remove this? If we remove this, then everything's pulled in this direction. And so with everything being pulled in this direction, this is going to go up, but these are going to go down. And so we were asked about H2SO4. The answer would be it would decrease. If we do that, everything is pulled to this direction, and therefore that would go down. So there's our answers. Number 7, the following reaction reaches equilibrium. And here we're looking at what happens if we increase or decrease the pressure. So here we have all gases. In A, it says what happens if the pressure is increased. So if we increase pressure, we know that it's going to move away from where the most gases are. Here, you have 1 plus 4 is 5 moles of gas. So we have 5 moles of gas here. Here we have 3 moles of gas. So if we increase the pressure, it's going to move away from this side. These two are going to go down, and these two are going to go up. And it asked about what will happen to the concentration of H2. It'll go down. So the answer is it'll decrease. And then what will happen to the concentration if the pressure is decreased? So if the other one, we increase the pressure, it moved this way. If we decrease the pressure, everything's going to move in this direction. This is going to get higher. These are going to get lower. And so we were looking for H2S, which is here. So it's going to decrease because when we decrease the pressure, it's going to move back towards the side with the most moles of gas. Therefore, these two will decrease and these two will increase. And then he was looking for this one. So the answer is decrease. What is the equation for the acid ionization constant of HCHO2? Okay, so we have HCHO2, and when we write this, it would be aqueous, and we are going to put it in liquid water, and then this is an acid, so it's going to give a hydrogen here, so this is going to end up as this. And this will have lost a hydrogen. It's negative. It's lost the proton, so it's going to be negative. There we go. So that's the basic reaction that you're supposed to have memorized. Then you write your acid ionization by writing this into your equilibrium equation. Don't forget your signs. They have to be included, or it is incorrect. There you go. So that would be the equation for your acid ionization of HCHO2. This part, right here. I showed you the equation so you knew where that came from. Notice this is a liquid, it drops out. That's why it's not written here. Number 9 is what is the base ionization constant for C2H7N? C2H7N. And once again, that is aqueous. We are going to put it in liquid water. And this is a base, so it's going to receive a hydrogen. So this is going to become C2H8N. This lost the hydrogen. This gained the hydrogen, so it's going to be positive. That lost the hydrogen, so it's going to be negative, and you have to have that information in there. And then you're going to do the base equilibrium. Don't forget your signs. Liquid water disappears again. There we go. And so that would be the base ionization constant equation. Number 10. The Ka for oxalic acid is 5.9 times 10 to the negative second molar. The acid ionization for nitrous acid is 4.6 times 10 to the negative fourth molar. At the same concentration, which produces a solution with the higher pH? Okay, so the first one is 5.9 times 10 to the negative second molar. And the second one is 4.6 times 10 to the negative fourth molar. So, and we're told they're at the same concentration. At the same concentration, this has a higher number for its acid ionization constant than this one does. And if you rewrote these, and you actually looked at these two digits, but you can see this. This is a larger number than this one is. So this is the stronger acid of the two. And therefore, the stronger acid would have the lower pH. Remember, acids are from 0 to 7, and the closer you get to 0, the stronger the acid. This one is the stronger acid, therefore it would have the lower number pH-wise. This one is the weaker acid, it would have the higher number pH-wise, and it says which produces a solution with the higher pH. It would be this one, because this one is the weaker of the two acids, because it's got a higher acid ionization constant. You are at your last test. Praise the Lord for high school chemistry, and you've done a great job by doing all this. Please go ahead and study for and take this test, and then you're going to grade your test online, and just keep your eyes on Jesus, because he is the author and perfecter of our faith, but he is also the only hope that we have. The only way to God is through Jesus Christ, the way, the truth, and the life. God came in the form of man. He died in our place. And why did he do all that? He raised 3 days later from the dead. Why did he do all that? Because he loves us. It's all about love. So if you've never entered a personal relationship with the Lord, you not only have to believe, you have to receive him as your Lord and Savior by faith. And then everything in your life changes. So I pray that you know Jesus. And if I could ever be of help to you, get in touch, let me know. Have a very blessed week. Have a very blessed life.